Проверьте, что мы в эфире сейчас. Ну что? Нет, я доску не поставил, да, я понял. Теперь мы появились-то. Ну, сейчас.
Не, ну да, все идет,
Ага, хорошо. Отлично. So today I shall speak about integer extensions and theorems related to it. Да? Going up and going down theorem. Well, and I shall explain what it is, of course. Yeah, so what means going up and going down. So this is some kind of geometric statement, and what should we know about? Yeah, so first of all, I need to say some comments that were made previously. So first of all, so suppose you have a ring and a prime ideal. And we can consider localization. Yeah? So we can consider localization. And what is important about this, we have that after localization, if we have P, it maps, so you can consider P times AP. Yeah, so that take this ideal in, so map it via, so you have a natural map between A and AP. Yeah, so you can take the image of the ideal, so of course, less symbolically, this should be written that as I of P, so you take the ideal P here, map it in the localization and generate the ideal. Yeah? So notice that this ideal is maximal, and this is only maximal ideal. Yeah, so this is only maximal ideal in the ring. And such ring is called local. Yeah, so just A is called local, so it's called local ring if M is a unique maximal ideal. So so notice that this why this is the only maximal ideal. Yeah, because we have considered localization, and we understood how ideals are changed under localization. Yeah, so that we had the map, if you take as a multiplicative set, which is A without P. Yeah, so we have considered spectrum of AS, and it was identified with a subset of P inside spectrum of A such that P intersection with S is M. And notice that if you look what ideal survives, yes, so the only, so this says that any Q, so if you have, so if S is equal to A without P, yes, so this intersection for Q Q is in spectrum, and you say that intersection of Q with S is empty, where so this is equivalent to say that Q is inside P. Right? So after this localizing procedure, P becomes maximal ideal, and any prime ideal is contained inside P, and all maximal ideals are prime. So this tells us that P is only maximal. Yes, so since all maximal ideals are prime, and any Q sits inside any Q prime sits inside P in AS. So this implies that P is only maximal ideal. Yeah, so notice also I want, maybe that will be. Yeah, so later, so the reason of one of the reasons that we are using localization, that you can make out of the ring, you can make a local. And also we had the important lemma about the integral extensions. Yeah, and notice that if you have A is local, yeah, you have automatically a field related with it. So this is a field. Yeah? So then we had the important lemma that I want to recall. So lemma. Suppose you have a ring and a subring, and B is the main, so it doesn't have zero divisors, integer, and then if A is a field, so and B is integer over A. Yeah, so meaning that any element of B is integer over A. So if A is a field, then this implies that B is a field, and vice versa. Yeah, so just if so let me write it down like this. So so I was writing it in two sentences because in order to say what we are proving, yeah, so that it is easier to say that we are proving part one instead of indicating direction. And so if you have, so this lemma will be crucial for us because it will allow us to distinguish maximal ideals. Yeah? So so let me now formulate going up and going up lemma. Yeah? So just so this is as follows. So suppose suppose you have I shall write it down just symbolically, and then I shall write the statement of the lemma. So the idea is the following: suppose you have integral extension, so integer extension. So as before, so B is the main, and any element of B is integer over A. Then you have, so here you have, so suppose you can take a prime ideal. So for any prime ideal P, there will be an ideal that is lying over this B. Yeah, so there exists beta prime ideal, and lying over in this setting means that simply that so such that intersection of B and A is equal to B. So let me just formulate it here, so that B is domain, A inside B, and B is integer over B. So suppose P is a prime ideal in A. Then there exists beta. It's B prime ideal. Such that beta intersection with A is equal to B. Yeah, so why such a thing is important? Yeah, so because so I shall say geometric interpretation. So need without much comments. So notice that if you have, so suppose you have a morphism between varieties, so morphism between affine varieties, and then you can think of, suppose you just have a continuous map, and you are saying that, for example, preimage of closed set is closed. So here, the closed subsets in x and y can be considered as a subsets in some affine spaces defined by the polynomials. Yeah? And one can introduce the regular maps, for example, as follows. So you just say that yeah, so f is regular. So this is a class of maps that is just that we should call algebraic, and this is a class of maps between affine varieties. So if there exists m and n, so such that ux is embedded into some a m, and y is embedded in some a n, and you have this means that x and y are realized as the roots of some polynomial system. And here, we say f is regular if this diagram is commutative, and for this map, big F is given by polynomials. So f is given by polynomials. So simply you have just f is so you have collection of coordinates here x1, xm. And simply you are writing down f1 polynomial of x1, xm. So in order to give the map between affine spaces, you should say so how you map a point and you map it in n coordinates. Yeah? So you are saying that the coordinates depend as polynomials. Yeah? So This is called regular map. And this suggests the following. So if you have, so here you have some variety Z defined by ideal I of Z. So you can ask how we can define preimage. Yeah, so notice that this so you are asking how you can define preimage by some ideal. Yeah. So this is done as follows. So you take yeah. So first you notice that there is so if you have a map between varieties, then you can map functions on Y into functions on X, and we are just saying that if you have so suppose you have phi as a function on Y, yes, so you take so you call it a pullback of phi. Yes, so this is a new function that will be a function on X, and in order to say what is this function, you have to calculate it on the points X, and you define it simply by composition. Yes, so that you are saying that you are taking phi of f of X. Yes, so that that can be said simply that if you have a function from Y, yeah, which is phi, yeah, so the function is just a map to A1 to a fine line, yeah, so to the coordinates, and you take one coordinate to be the coordinate on a fine line. So you may think of this new functions, so you have to construct the functions on X, and you can do it via composition. Yeah? So this is precisely the pullback, what we call a pullback of phi. And the thing is that this pullback map either works also, so you can consider regular functions on X, which is just if X is given by the collection of equations, you just restrict polynomials on a fine space to X, and you may say that you have you may notice that so this is a set of regular functions. Yeah, so if X is given in the fine space, yeah, so you by collection of polynomials.
Простите,
Ага.
тут кажется с трансляцией что-то не то, нужно, видимо, другую камеру переключить.
Камера?
Да, она сейчас, я покажу, как
Да,
выглядит.
правильно?
Ну вот, она просто вот так вот выглядит, то есть там как бы в маленьком уголке идет действие.
То есть, я не ту доску поставил. Вот так. Все понятно. Спасибо, что переставилось.
Сейчас проверю.
Yeah, so if X is embedded as simply by collection of polynomials, f1, fk, yeah, so these are...
сейчас хорошо стало.
Спасибо. Then you can say that kfx is just a restriction of this the polynomials of on am to x, which is just k of x1, xm, so the polynomials, and the restriction is obtained via taking quotient by ideal ifx. And we see that the pullback map maps kfy to kfx. Yeah? So that in fact the pullback is defined on the set of any functions on X, but one can prove if F is regular, then the pullback map, so when F is regular, you have a map from regular functions to regular functions. So in general, the regular functions can map just to the functions on X if F is arbitrary. For example, it can be not continuous a priori. But if F is regular, actually, if and only if the pullback map just maps the regular functions to the regular functions. And this is, of course, homomorphism of the rings. Of rings. And yeah, so you may think of so how you can define ideal. Just you have Z here inside Y, and then you try to check. Yeah, so Z suppose is given by the collection of equations, and you want to check that the point on X lies in the preimage of Z. Yeah, so X lies in the F inverse of Z. Yeah, so then in order to check this, you have to map. That means that it holds if and only if F of X is inside of Z. And this is checked via these functions. Yeah, so this holds for if and only if gi of F of Z is equal to 0 for any I. Yeah? And or just you can say that g of F of X is equal to 0 for any g inside ideal I of Z. Yeah? So the gi's are generators of the ideal, but you can check this either for generators or for the all elements in the ideals. For example, you can pick all elements of the ideals for as generators. And then you see that this thing is nothing as the pullback map of G. So this means that just the pullbacks of GIs are a collection of generators collection. So this is a collection of generators for F inverse of W. Yeah? So this means that to define F inverse of W, yes, so you have to take ideal I of Z, map it via F tilde star, and this won't be ideal inside our KFX. So you have to generate the ideal, and this is nothing as extension of the ideal. Right? So this is a geometric interpretation of an extension of the ideal that we haven't discussed. Right? And also there is so you can do it, so you can try to solve the other problem. Yes, so you have something inside X. So define W, yes, so I of W, defined by ideal here, and you want to consider F of W, yeah, and you want to say you want to define ideal of F of W, but there is a slight issue here, yeah. So the problem is, so notice that the issue geometric here, we didn't have, so here we have the following issue. Yeah, so the preimage of, so if Z is a closed subset, so it is defined by polynomials, the preimage of Z was also closed, it was also defined by polynomials from the algebraic point of view. But if you take this collection of polynomials and consider them as the collection in X, notice that they do not form ideal. So you apply the procedure of making ideal. You generate ideal by this collection of polynomials. And here there is also there will be funny issue also related with it because the situation will be vice versa here. So let us try to do it. So the exercise is the following. So so notice that the image of this, if this set is closed, this is not closed in general. So warning, let me. So f of w is not closed. Closed in general. And the example is very easy, so you may consider the hyperbola, so xy equal to 1, and take the corresponding, so it is a subset in A2, a closed subset, and you can map it to A1, but if you map it, so it will map, so any point z here, any point x here, has the preimage, so it can be mapped to x 1 over x, but the 0 point so cannot be inverted, so all points has the preimage except 0. So and what are closed subsets on A1? Of course only the sets given by polynomials, and if but polynomials in one variable, they form a principal ideal, and the one polynomial has only finite number of roots. So the principal, the generator of principal ideals has only finite number of roots. So this shows that only finite number of points are closed subsets on A1. And here we want to say that so here we have to do the following. So we have to consider the set of functions that vanish on the image. So let us denote it like this, so that the sets of polynomials that vanish on the image, and you're saying the following. So phi on that is inside k of y, it is phi is 0 on f of w. So notice that if you take so you can take phi here, and you can take the pullback. So the pullback of phi is just you can take the sets of zeros of phi, and if you take the pullback, as we noticed already, so that we have noticed that the preimage of a set of zeros is given by the pullback of the function. So this preimage in x is given by the function by f star of phi equal to 0. And of course phi vanish on f of w, so phi is equal to 0 on w if and only if if and only if the preimage of sets of zeros contain w, so that preimage of phi equal to 0 contain w, the set w. And this of course means that the condition of, so this condition can be rewritten as follows. So that is equivalent to say that f star of phi belong to ideal I of W. And this, of course, means that you are just that the closure, ideal of the closure, f of W is given by taking, and this is condition is just taking pre-image. Yeah? So you have homomorphism. So you have KFY that maps by the pullback to KFX. So here you have ideal I of W, and you are saying about which elements maps here and are in ideal W. So this is just pre-image, so you have to take f of star, take pre-image and take pre-image of I of W, which is operation of contraction of ideal. So this tells you that operation, and notice that taking, if you have inclusion, of course, of A inside B, so yeah, so then operation of contraction, so, and you have ideal here, beta, yeah, so operation of contraction is just taking, so this is taking pre-image and the inclusion, but this is nothing as intersection of A and B. And this tells you that geometrically, yeah, so the inclusion of the rings corresponds to the morphism of algebraic varieties. And this intersection, so finding ideal on the intersection is the following. So we have the following geometric intersection. So you have x, and the functions on kfx correspond to b. So it has a map to y, and the functions on y correspond to a. And we are speaking about the following problem. So here we start with the ideal here corresponding to, so here you have ideal pi, so corresponding to the sets of zeros, and this is z, and we are searching for pre-image. Yeah, so you have z here. And we are, so that correspond to ideal phi, and we are searching for pre-image that maps to z. Yeah, so we want to find just find W such that, so that corresponds to ideal beta such that f of W is equal to z, but so here f of W can be not closed, so we are saying that the closure of f of W is equal to z. Yeah? So that's why such statement, which is simply just the intersection of the ideals with the rings, is quite important, and it's just it really worth considering. Yeah? So because it is this is actually so if you think of this, if you want to apply it for points, then for example when z is defined by maximal ideal, this corresponds to surjectivity, because pre-image of any point will be so comes from the so there will be something that maps to the point. The point is closed itself, so this kind of this kind of statement, if z is a point, is equivalent to that the map is surjective. Okay? So let me just start with a discussion. Yeah, so let me say the proof of going up there. So going and the proof, there are essentially two proofs, and I have, for me when I first, when I would say I was rereading the proof, yeah? Yeah, so there are two proofs, yeah? So one is given in I.T. MacDonald book, and the other, for example, is given in the lectures of Gorodentsov, or in Matsumura books or whatever. Yeah, so you can find it in many places. And when I was reading the book of the proof in the book of A.T. MacDonald, I thought that it was incorrect. Simply because I couldn't understand how it worked. I mean, just so it was so simple that I was going step by step. I could check it, but I didn't understand why it really worked because there was some kind of strange arbitrary choice. And so I shall try via this geometric interpretation that we discussed, I shall try to explain why this arbitrary choice really makes sense. I mean, why this after this arbitrary choice, you really should come to the solution. Yeah, so the idea is first to do the following. So suppose you know the idea is actually a localization. So, but here you have to choose how you should localize your set. So you want to find the ideal here. So some ideal beta that we don't know. So that ideal here. But notice that yeah. So let me just write down symbolically. Yeah, so also notice that when you're speaking about finite morphism, so geometrically you should think about the morphism that has a finite number of, so any point has finite number of pre-images. Yeah, so this is spectrum of A, so this is spectrum of B, and this this picture of mapping spectrums, yes, so that symbolically I have really showed it here that the map between varieties x and y gives you the map between the rings in the opposite direction, yeah. And notice that if you have a map between varieties, yes, so what are prime ideals? Prime ideals are irreducible varieties. And you map the set of irreducible varieties to the set of irreducible varieties. Yeah? So, the geometrically finite morphism is you take a point, you take pre-image, and over this point you have only a finite number of points. And when you are proving something, you have to think about this kind of situation. So, but notice that so going up theorem is slightly stronger than what we were discussing, because usually when we're speaking about affine varieties, we're speaking about finitely generated algebra, because we take the affine space and take the polynomials and take the ideal generated by these polynomials. And you may use Hilbert basis theorem that tells you that the ideal is finitely generated. And here you also we're speaking about finitely generated algebras, because when you have x is embedded in AM, there are finite number of So then the set of functions is obtained as follows. You take the polynomials and you factorize them by ideal, but the variables itself are generators of the polynomial ring, and the images of these variables are generators of kfx as the algebra. So you see that the algebras that come from starting algebraic varieties are finitely generated. So yes, so let me finitely generated algebra over K. It looks like tautology, but when you are trying to prove something, it's not. I mean, it is important. So also I want to make out of P a maximal ideal. It happens that notice that what does it mean? That for example, if you are thinking about collection of by the way, if you are speaking about even if you are speaking about if P is maximal, so remark. So even if P is already maximal, the operation of localization also makes sense. So the only difference is that between more general operation of localization, that P could be not maximal a priori, but then after localization it becomes maximal. But here in A, there could be several maximal ideals. After you localize, this has only one maximal ideal. So this means that maximal ideal is notice that if you have inclusion of varieties, the inclusion of ideals is opposite. So maximal ideals correspond to the points, usual points on your variety. So the maximal ideal corresponds to the minimal possible variety with respect to inclusion, and minimal possible variety with respect to the inclusion is by definition a point. And this means that after operation of localization, so you could have several points outside P. And after localization, they're simply killed. So you just throw them away geometrically. And this suggests the following. So if so this suggests to make this localization, yeah, and find so to try to find yeah. So let me so put S to be multiplicative set. So put S to be a without P, and consider the localization of AP, which is AS, and also you can localize B by S. Yeah, so that's why I have written S as multiplicative set, because P is no longer an ideal inside B. So I'm just taking the multiplicative set and A, consider it as a multiplicative set, and can localize it. And notice that we have, so what is geometric meaning of, so if you have, geometric meaning of localization, if you take only one function, so S is equal to 0, yeah, so let us recall that what ideals are killed when you consider this localization with respect to one function. Yeah, so if you have A, then you take a S. Yeah, so if you take prime P that was not inside the S, so just P correspond to the variety Z. Yeah, so that Z was not entirely contained in the set of zeros of S. Yeah, so this is equivalent that S was not inside P. Yeah, so just this is by definition, and such P survives. P also belongs to. So P gives you element of P gives you non-trivial element of the spectrum of localization. Yeah. So is a non-trivial prime ideal. And if you have P, so when P is inside your set of zeros S, yes, so that means that, so if P corresponds to Z, that is entirely inside S. This means that S intersection with P is not empty, yes, so that S belongs to P. S is a generator of the multiplicative set. Yeah. So I meant like this. So then S belongs to P. This implies that just PAP is empty. So PAS is just AS. So this P doesn't give you anything from the viewpoint of ideals. So localization with respect to so to the element is just throwing the set of zeros of this element. Yeah? And notice that if you have several elements, this means that you're just throwing the points corresponding to these generators. So it is not very difficult to understand that localization with respect S of the ring B is just throwing away the set of zeros of, so you take the equations here, just S, and you throw away the preimages of this sets of zeros. Yeah? So you have to take F star, so you have F here, the map, so you have to take F star, the homomorphism of F, and you throw away the sets of zeros of these functions. And this means that if you have thrown away the collection of points outside of P, you have thrown away the collection of closed points outside of outside of preimage of P. So the only thing that has survived here, downstairs only P has survived as a point. And well, if you are speaking about maximal ideals, then subvarieties that are contained in. So if P is not maximal a priori, then subvarieties of P will survive. And so subvarieties that contain P has survived, and ideals that are contained in P have survived. And if you are speaking about P when P is a point, P is survived, and only preimage of P survived, and other points were just thrown away. So if you are speaking about real points, then P is correspond to the maximal ideals, and preimages over P correspond to the maximal ideals. Yeah? So now I shall notice. Suppose that we solve the problem for localization. Yeah, so assume we find beta tilde in BS such that beta tilde intersection with AP is the following. So this is just the image of P under localization. Notice that B has no zero divisors a priori. Yeah, that's why localization is just inclusion. Yeah, so we have inclusion of the. So we can just speak about this thing. So notice that just we proved that the intersection of P, so the intersection of PAP and the ring A is just P. Yeah, so we can recover P by taking the extension of the ideal and the intersection. So let us note, so now we have to calculate this thing. So we want to intersect the beta tilde. So put beta to be a intersection of beta tilde and B. So notice that beta tilde, beta was prime. So we assumed that we could solve the problem. So we could find such beta tilde which is prime, and this intersection is PAP. So note that beta tilde is prime.
Сейчас, может быть, бита тильде, оно лежит в локализации?
Да, извините, да, локализация. Спасибо. Вот, beta tilde is prime, then beta tilde intersection with beta is also prime, because pre-image of prime ideal is prime. Yeah? So the only thing that we need to check is that intersection of beta and A is our ideal P, but you are writing down this as beta tilde intersection with beta and intersection with A. Yeah? So, this can be written as follows. So we can take intersection of beta tilde, first intersect with AP. First intersect beta tilde with AP, and then you can intersect it with A. Yeah? And this, if you intersect beta tilde is with AP, it is by definition by the choice of beta tilde PAP, and you intersect with A, you just take P. Yeah, so that is easy, and clearly this gives you the solution. So now we can assume the following. So now on, assume that P is maximal. Yeah, so just P is maximal inside AS, and you just here A is local, but I think this is not important. We shall see that. Now I shall prove that. So we prove going up under this statement assumption. So going up under this assumption. And when we have proved it, yes, so you can apply proofs. So just how we can find beta. So take for beta any ideal, any maximal ideal in beta. In B. So this is really embarrassing because I mean if you take unrelated rings and you take any max, I mean if you take the situation which is not in our case, yes, so you this is something as the following. So you take so you want to find pre-image, so you want to find pre-image of 0, yeah. And I'm saying that if I'm taking any ideal, I take any ideal corresponding to the point here, and I claim that it will map to our ideal. Yeah, so you so here the claim is that the beta intersection with A is equal to P, but I mean, in any in any almost in any geometric situation, this is stupid. Yes, so you want to map inside this point. You take any arbitrary ideal. It should map actually to the other point. Except this case that we have done in our reduction, we have killed all the points by this localization that are that are not in the pre-image of our ideal. And now, so now let me я не там поставил страницу. No. So now we just take B, so you have here ideal P. So you have taken beta, but so now we take intersection of beta is maximal, yeah? And the P is only maximal ideal, so only maximal ideal in A. So we have the following situation. So take intersection of beta and A. So notice that this is so this is some ideal. This is you can call it P tilde. So this is prime ideal in A. Prime ideal in A. But so how we can prove that we want to prove so it is not related at all with P, yeah? But we want to prove that it coincides with P.
Значит, а почему это вообще идеал?
В смысле, пересечение идеалов, ну, прообраз идеала и идеал. То есть пересечение с подкольцом. Ну, потому что вы, под кольцо вы можете, ну, это условие аддитивно, и вы можете умножать на любой элемент из А. Да? Ну, потому что элемент из А является, в частности, элементом из Б. И он также простой, это мы тоже показывали. Потому что, ну, вы можете проверить, что, ну, как бы вот это условие простоты. Другое дело, что, ну, как бы, если вы пересекаете идеал с кольцом, он не всегда максимальный, и в этом, ну, как бы, вот, есть проблема. То есть это вы можете привести пример такой. Вот. То есть даже если вы стартовали с максимального идеала, пересечение может не являться максимальным. When you are speaking about this, when you are speaking about this thing, so you have to, but how to prove that P could be prime? But you have to use that P is the only maximal ideal. So to prove that p tilde is equal to p, it is sufficient to prove that p tilde is maximal. And now let us use this lemma that we have learned. Yes, so notice that, so remark, if we have started with this situation and where b was integer over a, and the S is multiplicative system inside A. Then ES is integer over BS. Yeah? Just because you can use the same polynomial for integer element. Yeah, so any element of B satisfies the integer polynomial, you can use it as a polynomial after taking localization. And if you are, so if you have this thing, then also, yeah, so you know a priori that in our case that we assume that b is integer. So here we assume that, so in our special case where p is only maximal ideal, we also keep the hypothesis, so keep the hypothesis that b is integer over a. And also we can do the following. So we can consider the quotient of b to b by beta, so let us denote it by pi. And notice that if you look at A, yes, so inside it, yes, so the image is will be of A intersection. So the subset in the quotient, the image is just A modulo the restriction of kernel of pi to A, which is just, and the restriction of kernel of pi to A is just taking the kernel and intersect it with A, which is just a beta intersection with A. So this is just A mod p tilde. Yeah? And notice that P was, beta was maximal. Beta is maximal ideal. Yeah, and then beta mod B is a field, and A mod p tilde is integer extension of B mod beta, because again you can use the same integer equations. You can reduce it modulo the ideal. So this implies that A mod p tilde is a field. So P tilde is a maximal ideal. And we are done. Yeah, so that this proves the statement because since again I shall repeat it that since P is only maximal ideal, in A. This implies that P tilde is equal to P. So it's only non-trivial maximal ideal. Yeah, so that of course, yeah, so it may happen that P tilde can be zero. So sometimes zero is maximal ideal, but this holds precisely in the field. So yeah, so by assumption, by definition, maximal ideal is the ideal that doesn't coincide with the whole ring. So yeah, so this shows the statement, and there are some. So we can think about some corollaries of the proof. So let me. So the proof is finished.
Секунду, мы
Да.
не для случая, когда только максимальным идеалом по изначально является.
Да, но мы изначально, помните, первый шаг у нас
Да.
был это локализация. Локализация по P. Вы взяли P,
Ну да.
локализовали по P, но значит P стал единственным максимальным идеалом. А потом мы сказали так, что если мы знаем вот после
Нет, дальше.
того, как локализация, то мы можем просто взять после операции локализации, пересечь наш найденный идеал, вот этот дойти до
Нет, дальше понятно.
То есть, so here there is a corollary of the proof. That so suppose that B is an integer extension of A. P is a prime ideal. And suppose beta 1, beta 2, so you have inclusion of two ideals are a prime ideal of B. In B, such that you have two prime ideals, one sits in the other, and the intersection with A is equal to each other and equal to this ideal P. Yeah, so actually you do not need in the formulation. You do not need this. Yeah, so you do not have to say anything about this prime ideal A. So I just wanted to say that just how it was related with previous notation. Yes, so we have two ideals with so that they have one was inside the other, but their intersection with A are equal. So then I claim that the ideals were equal before intersection. And so the proof is the following. So proof then you put again. So again, we have to do this. We have to. Yeah. So geometrically, this means the following. So that when your morphism is finite, yeah. So and you have some subvariety here, some irreducible subvariety. You cannot have the following situation that you have two irreducible subvarieties that maps finitely to your given variety P. Simply for or just, of course, in more general settings, suppose it can happen. Yes, so if the fiber has non-trivial dimension, yes, so and it maps to the point, for example. Yes, so that is maximal ideal. Yes, so you can imagine that you have the fiber of non-trivial dimension. So and you have at least point on the fiber, and so you have a reducible variety that maps to the point, and the point that maps to this point. But when you have finite morphism, of course, I claim that this is not possible. Yes, so that you cannot have because the dimension of the variety, you can just calculate namely the dimension. If you know that, for example, something is manifold in a general point, and this is the case when you are considering the map between algebraic varieties, then the finite morphism is just analog of, so this is ramified covering, and over a general point, the preimage is just ordinary covering. So the theorem more or less tells you the following, that since any point has preimages which is just a finite number of points, yeah, it tells you that the dimension of the preimage is the same. And since the dimension of the preimage is the same, you cannot have this kind of picture. You cannot have inclusion of reducible varieties into each other of the same dimension. And so let me say how to prove this. So suppose, so again, to put S to be a multiplicative set. So put S to be A without P. And so localize, yes, so pass to localization, AP and BS. And notice that in the localization we have proved that if you have two ideals, just considering, so if first of all, if so notice that beta i's, if you the intersection with S is empty, so since just beta I just intersection with A is equal to precisely P. Yes, sorry, I haven't written that P is equal to beta 1 intersection with A and beta 2 intersection with A. So put. So since and localized by this multiplicative set, so since you have this intersection, the intersection of beta I with S is empty. So if the ideals are not equal, so if beta 1 is not equal to beta 2, this implies that after localization, beta 1 beta S is not equal to beta 2 beta S. They are both prime. Yeah? So these are both prime ideals. And after you have localized, so you get the following. So you just you are in the precisely in our case that you have two ideals. Yeah, in beta S you have two ideals. Beta what was larger? Beta 2 was larger. Yeah? So beta 2 and beta 1. Yeah? And notice that so here you have AS. Yeah? So you have P. And notice that you can factorize by beta 1. Yeah? So pass. So take BS factorized by beta 1. And by our, so since P was equal to intersection of A, S and beta 1, yeah, so BS is integer over A S mod P, and since AS is AS mod P is a field, yeah, notice that now BS mod beta, so since beta 1 is prime, it has no zero divisors. Yeah, so there are no zero divisors. Since beta 1 is prime. And after localization, they're still prime. Yeah? So now we have taken this quotient. It is integer over AP. So if so, since this is a field, this implies that beta S mod beta 1 is a field. And this implies that there are no ideals, no non-trivial ideals. In beta S mod beta 1. So this implies that beta 2 is equal to 0. And in beta S mod beta 1, so this implies that beta 1 beta S is equal to beta 2 beta S, which is contradiction. So this proves the theorem. So yeah, and so this yeah. So now I want to make a break, and before, so I want to emphasize that it was really a miracle, yeah, because the proof was some kind of miracle, because it seems that you have done some operations. And then after doing this precisely this special operations, you did an arbitrary choice, yeah. But it is like that you were searching for just for something, but you put yourself in some circumstances that allowed to find your thing, yeah. So your ideal. And so after the break, I shall speak about. Going, yeah, so I shall say the generalization of Going theorem, which is really will follow instantly from this theorem, and I shall speak about going down, which is more complicated theorem. Ну что, 10 минут, да? А, окошко откройте. Ну дайте, да. Да.
Немножко такой присоединяюсь к курсу. Я находюсь на математике. Такой вопрос, я так понимаю, листки выбираются.
Не, еще пока нет.
Пока нет.
Я хотел как раз, на неделю.
Хорошо. И хорошо, а где они будут появляться?
В Телеграме. То есть там и как бы записки лекций тоже.
А мне, видимо, нет в чате курса, можно им как-то добавить.
Ну да, давайте.
Можно найти.
Ну, 925, 349, 920. Тогда сейчас просто добавлю.
написала. Спасибо большое.
Да, не лампу. Ну что, продолжим? Да. Да, ну давайте теперь посмотрим, что можно из этого вывести. Ну, so consider the following situation. So you have the following extension, and you notice that you can take a sequence of prime ideals here. And notice that you can, actually the question is more or less about two ideals. So suppose you have here P1 and here you have P0 prime ideals. And you can ask yourself of constructing ideals beta that is consistent with this picture. But suppose you have constructed beta 0 already. So you have constructed. So we want to extend this diagram. So we want to find beta 1 that those intersection with A will be P1 and it will contain beta 0. So and this is called going down, going up. Because going up, because you go up, so so you go up this just if you have fixed this ideal and this ideal, yeah, so you in order to find beta 1, you go up from with respect to inclusion. То есть, ну, как бы ситуация такая, что мы хотим, ну, вот начать с, у нас есть уже цепочка пиитов, да, в А, и вы хотите как бы начать строить цепочку над ним идеалов, таких, что пересечение бета-итов с А как раз вот совпадает с этими пиитами. И это можно как бы делать разными способами. Можно стартовать, ну как бы строить под такие цепочки, казалось бы. Можно стартовать с бета-0 уже, как будто вы построили. И вот пытаться построить бета-1 с такими свойствами, которые содержат уже бета-0. И вот теорема как раз going up, она говорит, что вот можно построить вот эту бета-1. Давайте я это напишу в качестве теоремы. Что so suppose B over A is integer extension. When I shall write integer extension, I shall mean that B has no zero divisors. And then so suppose that beta 0 inside B is prime and P1, P0 inside A are prime such that beta 0 intersection with A is equal to P0, then there exists beta 1 inside beta which is prime such that beta B intersection with A intersection with beta 1 is P1. So, and the proof of this theorem is really easy, yeah, because you just reduce it to the previous case where P0 is just 0. Yeah, so how to reduce it? Yeah, so consider the quotient P of beta to beta B modulo beta 0. Yeah. So when you are looking about on its restriction, it maps to A modulo kernel of pi restriction to A, which is just A modulo beta 0 intersection with A, which is just A modulo P0. So you see that P of P1 is prime, so prime ideal. Yeah, so you have to prove it. Yeah, so the tangent is surjective map. So this is a prime ideal, and then so this is just P1 quotient by P0. And this is because it contains kernel, it is prime. So this is actually an exercise. Yeah, so exercise. So when you prove it that it is prime, so it is now sufficient to find beta 1 tilde such that so beta 1 tilde and beta mod beta 0 such that beta 1 tilde intersection with P0 is equal to, yes, we can call it P1 tilde. Is equal to P1 tilde, and put beta 1 to be just a pre-image of beta 1 tilde. So this is straightforward. So you can reduce everything by taking the quotient. Что-то произошло. Просто.
Видимо, просто что-то зависло.
Да. Ну, в общем, если мы посмотрим на вот эту диаграмму, да, что мы можем просто факторизовать по бета 0, а на уровне, когда мы ограничиваем на а, это приводит к факторизации под p0. Поэтому мы просто про этот кусок забываем, и мы пишем без условий на условия на бета 1, потому что вот это условие вложения это как раз и есть, ну, которое мы должны удовлетворить, это 0. Ну, любой идеал содержит 0. А вот как бы если мы захотим вот эту теорему как бы проговорить с другой стороны, вот сейчас я тут как раз бета-1 стильный. So if we want to do it in the opposite direction, so this is a little bit more complicated, yeah, because so you start with construction of beta 1, and you have to find here, so you have to find beta 0, which is which satisfies these properties. Yes, so that intersection of beta 0 is P0, and it should be contained in the given beta 1. And you cannot just take arbitrary beta 0, because a priori you will get another thing. So actually also you if you want to formulate the statement, so there is actually a counterexample to the statement. So let me just draw the counterexample. So imagine the following. So suppose so you have when you have nodal cubic, so it have a natural rational. Yeah, so it is just the cubic given by equation like this, as we have discussed. It has a natural rational parameterization. How just it is obtained. Yes, so we have almost written it. Yes, so we have taken the parameter t that is x divided by y, or y divided by x, doesn't matter. But yeah, so actually y divided by x, because it is just saying that. Yeah, so this is just saying the following. So you are just drawing the line. Just y is equal to tx, And you notice passing through this singular point, which saying that the point is singular is saying that so if you restrict it to the line, then you have the following. So this is given by the cubic polynomial. If you restrict this cubic polynomial precisely to the line, which you consider, you will still have the cubic polynomial. But cubic polynomial has at most 3 roots. So you see that this root that we marked, which is a double point, it has multiplicity 2, and the remaining root has multiplicity 1. So this tells you that if your t variable t varies along and you have the variation of the angle, then this point runs through all your the nodal cubic, and this gives you the so-called rational parameterization of the cubic. However, you have 2 points that map to the same point. This corresponds to to the cases when the line is tangent to in this double point, because so these tangent lines they play a role of triple lines, and this gives you this rational parameterization, meaning that when you substitute tx inside in this equation and you solve the equation for x, so this gives you precisely how you write down y of t. So you can write explicitly for this situation y of t and x of t, and this is called the rational parameterization, and this gives you the map from the fine line with 2 double points, with 2 points to this nodal cubic where these 2 points glue together. So this nodal cubic, so you can multiply this by the line and look at as the image of the following plane, where you have 2 marked axes. And then you can take the line, so you can mark the points that lie in the same point, and you can mark another pair of points, so which map to the same line, and you can draw the line passing through different type of points. How it will look like? So there will be a black point here, so the image of the black point, and this line will look like a curve that is passing like this, so and going on the other sheet. And notice the following. So if чем больше идеал, тем меньше многообразия, да? Поэтому, давайте вот как бы тут понятно, да, вот с этой картинкой все окей, да? Вот, а теперь давайте, как бы отметим, каким идеалом, вот это как бы, вот это получается большее кольцо, это меньшее кольцо. Вот это вот соответствует B, это соответствует кольцу А. Вот это вот отображение сюда соответствует вложению колец в другую сторону. И теперь мы, давайте посмотрим на геометрию. Да? Вот в качестве P0 и бета-0 мы положим, это прямая, да, вот это пусть будет соответствовать P0, а вот это бета-0. И вот как бы теперь мы хотим взять следующее, но теперь мы хотим вот как раз найти P1, и вот, но мы фиксируем P1 и бета-1 над образом, да? Но вот тут видно, что бета-0, ну если вы выбрали P0, то бета-0 однозначно выбирается на этой картинке, правильно? А вот с P1 понятно, что вы берете, вот можете выбрать вот этот P1 здесь, да? Вот, ну, как бы другого выбора нет. А вот здесь уже, ну, с идеалами, которые лежат над P1, тут есть выбор из двух. Поэтому, ну, вот, можно выбрать за бета-1 вот эту точку, а можно вот эту. Ну, давайте выберем, поскольку бета-1 заранее зафиксирован, давайте выберем не ту. Вот, давайте вот это будет бета-1. То есть мы видим, что отображение, конечно, сюррективно, то есть вот в точку P1 отобразится какой-то бета-1 с тильдой. Но это будет не то бета-1, которое вы исходно можете выбрать. Вот она, вот эта бета-1, которая сюда не отобразится. Эти две зря нарисовал, ну так просто для красоты можно считать. Ну потому что... вот. Потому что вот эта прямая все-таки в двух точках пересечет, да, вот эти вот две прямые. Но получается, что как бы вот при произвольном, ну то есть как бы вот эта вот ситуация, которая говорит о том, что вообще говоря, ну вот эту теорему в общем случае мы не можем ожидать. То есть надо еще наложить какие-то свойства на наши кольца. И вот этот, но мы помним пример чего был вот этот вот пример. Да? Это был пример нецелозамкнутого кольца. Поэтому в формулировке нужно потребовать целозамкнутость. Давайте это потребуем. So, theorem going down. So assume that B is, has no zero divisors. A is integer over B is integer over A. And A is integrally closed. But integrally closed in its fraction field. Yes, so in fraction field. То есть, смотрите, мы требуем целозамкнутость в своем поле частно, но это как бы, ну то есть это кольцо, которое построено по А. Не значит, что если вы рассмотрите А в большем кольце каком-то другом, это не значит, что что не могут быть целые элементы, которые А не принадлежат. Это вот как бы важно. И then so for any P1 P0 prime ideals in A and beta 1 side be a prime ideal such that beta 1 intersection with A is P1. There exists beta 0 such that beta 0 intersection with A is equal to P0. То есть, ну, как бы вот здесь произошло следующее в нашем контрпримере. Это, то есть, тут получилось, что ну вот как бы кандидат на бета 0, он однозначный, потому что по сути, ну, в общей точке, да, у нас вот это отображение просто изоморфизм. Вот, ну как бы, то есть, ну вот, поэтому как бы вам не нужно тут, ну вот эти все подъемы, они как бы более-менее автоматические. Но...
B0 тоже простой.
А?
B0 тоже простой.
Да. Только у меня... Да, спасибо. Существует бета 0. Но вообще вообще как бы сложная ситуация, когда у вас, ну, как бы нетривиальный морфизм, да, то, конечно, выбор бета 0, ну, может так случиться, что у вас есть выбор, да, ну, то есть фактически выбор происходит так: вы берете сам идеал, вы берете прообраз, ну, вы берете многообразие, вы берете его прообраз, и вот он, ну, как бы прообраз имеет ту же размерность. И значит, там есть несколько компонент разной размерности, вот вы как бы одной и той же размерности, и вот вы выбираете просто одну из этих компонент. Ну вот и как бы возможность выбора одной из компонент, это как бы есть эта теорема. Давайте ее докажем. Вот, но вы немножко же теорию угла знаете, да? Кто знает теорию угла? Ну да, давайте, вы не знаете. Ну вот, нужно знать только, что вот есть группа угла, которая действует, и все, и множество. Ну да, давайте я скажу. Вот, ну, тогда для вас доказательство будет просто схематичным, ну, как бы, для остальных, ну, как бы, ну, что-то. Давай. Ну, вот, как бы, тут есть маленькая тонкость, которая, ну, вот, давайте, so let us consider this extension. Yeah, so reduction, reduction to the Galois case, and the proof. So if you have two rings, yeah. So here you have fraction field of A. And you have fraction field of B. So here you may do the following. So this is K, this is L, and suppose so for simplicity. Suppose that the L over K is separable. I shall explain how to check it when it's not. And L over K is separable, and or if you just or even the characteristic of K is equal to 0. Yeah? So when you have such equal. Извините, перечеркнул. Ну, просто, чтобы как бы, ну, если вам тяжело думать про сепарабельность, просто считайте, что характеристика. Вот, so if you have this kind of extension, the trick is that you can extend it to the Galois extension. So the claim is that any field extension which is separable can be extended to the Galois extension can be Galois extension. And the trick is the following. So the trick, so how it can be done? So just L over K is defined. Is finitely generated. So it's obtained by adding some roots of polynomials. So alpha I are roots of irreducible polynomials. F1, Fn. And if how you can make out of this extension a Galois extension? The Galois extension is such extension where all the roots of, if you add one root of polynomial, all the roots of this polynomial are added. So just simply add all possible roots of this polynomial. So add all possible roots of F1, Fn. If already you're working in the algebraic closure, this is more or less trivial operation. I mean, or just you add all roots of them and that's it. So then this notice that if you have this kind of extension, you can extend your sequence of the rings So B is integer over A, you can consider C is integer elements over A. So we can consider the integer C, integer elements of L tilde over A. Now we have to fit this in the sequence of ideals. Yes, so if you have here, if you have P1, so just if you have P, yes, so there is always so here we have taken B line over P. Yes, so since C is integer over B, we can find the ideal line over B. So C is integer over B. So this means that there exists gamma ideal, prime ideal, gamma in set C, prime ideal, such that gamma intersection with beta B is equal to beta. So in our picture that we are looking at, yes, so you can find the following. So if you have So you can find over, so let us recall that. Yeah, so that we have here B, so here you have ideal beta 1, and you want to find, yeah, so here you have ideal P1, here you have ideal P0, here you have ideal A, and you want to find some ideal here. So here you have to find beta 0. Yeah, but notice that you already, so here you have C, here you have gamma 1, and suppose that we can find gamma 0 for P0. Suppose you can find, so assume we can find prime gamma 0 for P0, gamma 0 is equal to intersection with A. Yeah, so then of course we can put beta 0 equal to intersection of gamma 0. Yeah, and of course gamma 0 sits in gamma 1. Yeah, so that we can put, so we can put beta 0 to be equal to intersection of gamma 0 and beta, which is also prime. And since yeah, so notice that since beta 1 just is intersection of gamma 1 and gamma 0, beta since beta 1 just is intersection, beta 1 is intersection of gamma 1 and B. Yeah, so this of course, if since gamma 0 was contained in gamma 1, yeah, so this implies that beta 0 is contained in beta 1. Yeah? То есть, ну, как бы вот эти условия, они оказываются у нас автоматически удовлетворяются. Если мы находим вот это вот гамма 0 для P0, то бета просто автоматически как бы все следует. Но это как бы с точки зрения многообразия, да, это неудивительно, если мы здесь вот...
Автоматически в смысле из going up теорема.
А?
Автоматически в смысле из going up теорема, которую мы уже доказали.
Да, ну в смысле мы из going up нашли гамма 1, но если вот мы как бы знаем, что going down, то есть гамма 1 мы нашли из going up, ну как бы, но вот гамма 0 получается, если бы мы умели going down доказывать для C, найдя гамма 0, оно автоматически удовлетворяет требованиям, ну вот, и бета 0, который мы находится как пересечение гамма 0 с бета.
А нельзя тут напрямую применить going up теорему как бы для гамма 1 вложено в бета 1 и в p1, и, ну, короче, для части этой диаграммы, которая справа, например.
Не, ну going up, она
ну,
вот, она и наоборот,
она же
из
как
этих делает эти, ну как бы вот.
Ну, или же из бета 1 делать бета 0, то есть подняться...
Ну вот этот going down.
Ну, в смысле, посмотреть на диаграмму под углом 90 градусов.
Нет, но они же...
Ну, я понимаю, что это не совсем...
Нет, но вам же нужно,
что
чтобы
нужно,
тут было целое расширение, поэтому вы не можете
Ну,
поворачивать
да,
диагональ.
но это же вот просто такое же утверждение, значит, наверное, можно и going up как-то обобщить для чуть более общими свойствами, обладающими колец.
Нет, going up, она идет, ну, как бы вот эта вот строчка фиксирована, она идет вот так. Going up.
Мгм.
Ну, поэтому, как бы, вот вы, ну, именно, что у вас going up доказывается вот для, ну, вот этих расширений. То есть, ну, и мы видим, что вообще going down не может следовать из going up, потому что у going down есть еще дополнительные условия. В going up мы, если вы им никак не пользовались, то как бы вот и все. Но действительно вот это вот как бы расширение, оно соответствует, ну, вот, нахождению под многообразием в их стиле, да, поэтому тут просто и вот эти вот свойства быть простыми, это просто образ неприводимого многообразия не приводим, поэтому, ну, вот, если мы, что мы сделали, ну, вот тут были многообразия, ну, соответствующие там y1, y2, вот, тут было x1, которое мы нашли, вот, тут было x1 с тильдой, которое мы нашли благодаря going up, ну вот, для вот этого перехода, и вот как бы поскольку мы нашли вот это x0, ну, это x0 вот здесь с тильдой, да, то вот это вот получается x0, оно получилось просто автоматически как образ вот этого x0 с тильдой, да. То есть поэтому, ну, как бы, если у нас вот это есть сквозное отображение, то у нас просто x0 получилось как образ вот этого. То есть, как бы, с геометрической точки зрения это, конечно, все ну, просто, да. Ну, то есть с коммутативной алгеброй то тоже мы просто берем пересечение, ну, как бы, а с геометрической, ну, как бы, да, ну, даже не надо думать ни о каких проверках. Вот. Ну и теперь как бы мы можем пользоваться силой теории Галуа, но вот что нужно нам от теории Галуа? So, what do we need? We need from Galois theory, ну, совсем немного. Ну что как раз вот это К, это неподвижное поле, что если G это группа Galois, so if G is Galois group of L tilde over K, then the fixed points of G, so the set of fixed points, fixed elements, is precisely K. То есть, если мы видим элемент, который уже заранее по причинам инвариантен относительно действия группы 2, это наш элемент. И вот утверждение, что давайте so the proposition that we want to prove that Galois, so suppose you have the extension such that L is a fraction field of B and K is a fraction field of K. A is integrally closed. B is integral over A, integer over A. And yeah, so then Galois group, yeah, so the L over K is Galois extension. Galois extension. then G is a Galois group. And P is inside is a prime ideal. So then G acts transitively. On the set of prime ideals lying over P. On the set of prime ideals beta size beta lying over P. Yeah, so, ну давайте поясним, что это. So if you have beta 1 and beta 2 inside B such that beta 1 intersection with A is equal to beta 2 intersection with A is equal to P, then there exists sigma in the Galois group L over K such that sigma of beta 1 is equal to beta 2. Ну, это и есть транзитивность. Транзитивность — это переставлять элементы, ну, то есть переводить любой элемент в любой другой с помощью действия группы G. Вот как бы, ну, вот отсюда мы, поэтому нам нужно вот как бы было расширение БУА, и вот отсюда мы как раз потом выведем, ну, вот, нужное свойство going up. Но вот тут есть всякие мелочи, которые, ну, они технические, просто они требуют больше слов. Ну, например, как бы вот b над a может быть не конечно порожденным априори. Ну, вот как бы мы тут только используем быть целым элементом, все элементы b над целый над a. Ну вот как бы есть проблема, что ну как бы что вот расширение полей, они могут, это не конечное расширение полей. Ну вот давайте вот это вот проигнорируем. So let me technical simplifications. So yeah, so here yeah, so yeah, so technical simplifications that also B can be not finitely generated over A. So just assume that L over K is fine, is, so assume that it is less than infinity. So if you want to, yeah, so notice also that this observation tells you that you cannot have, so the previous situation where B, the previous corollary that both proved, we said that it's impossible to have beta 1 that sits entirely in beta 2. Yeah? So this, I mean, this, if this theorem, if that corollary wasn't true, then this theorem couldn't be true. Да? Ну, то есть, вот помните предыдущее следствие, которое говорит о том, что не бывает ситуация, что два идеала лежат над P, в чем один вложен в другой. Но вот если бы это следствие не выполнено было бы, то у нас не было бы шансов вот найти такой элемент сигма. Ну, это так, мелочи. Вот, ну, давайте докажем вот это, proof. So, how do we do it? Suppose you have beta 1, so beta 1 and beta 2, two ideals lying over P. So note that that by previous corollary, beta 1 is not contained in beta 2, and beta 2 is not contained in beta 1. So consider beta 1 and the union and the orbit of beta 2. Yes, so of course, so we have noticed that beta 1, yeah, so couldn't be inside sigma of beta 2 for any sigma, since the following holds, yeah. So since sigma of beta 2 is also ideal lying over P, so it is prime ideal because it is just an application of automorphism to the prime ideal, and also if you intersect this, yes, so if you intersect it with beta with A, this is equal to intersection of sigma of so sigma fixes elements, all elements of A, because it A sits in K, and K is by definition the fixed point set for sigma. Ну и мы получаем, что мы можем протащить сигма вне А, это сигма от P, ну и это и есть P, да? Хорошо? То есть, ну, как бы мы получили, что вот эти вот, если мы берем бета-2, он тоже лежит над P, то и вся орбита, все элементы над, ну, которые лежат, ну, все элементы орбиты, они тоже идеалы, которые лежат над P. Ну, тогда мы получаем, что бета-1, ну, то есть вот по предыдущему следствию, so by previous corollary, beta 1 sits inside sigma of beta 2 is impossible. Но если они совпадают, то как бы все доказано. Вот, я имею в виду, если они строго совпадают. So if beta 1 is equal to beta of sigma 2, nothing to prove. And Then let us recall prime avoidance lemma. So let me recall prime avoidance lemma. That tells us the following. So suppose ideal is contained inside the union of prime ideals. Then I is contained inside Pi, so these are prime ideals. Then I is contained in some Pi for some I. Но с другой стороны, как бы вот можно отрицание, так сказать, вот этой леммы, да, что существует элемент x из i, such that x is not inside pi for any I, for any I. So where pi are prime ideals. То есть у нас есть для конечного множества идеалов, да, всегда найдется элемент из идеала, но если и не лежит, то есть, вот это вот можно найти, если и не лежит в P для любого. То есть, как бы, если и не лежит целиком ни в каком P, значит, можно найти такой элемент, который не лежит ни в каком. То есть, как бы, так вот это условие, это существо для каждого и существования своего элемента, а вот это вот построение общего элемента, который не принадлежит никому. Но давайте вот этот вот элемент, поскольку мы получили. So since beta 1 is not inside sigma of beta 2 for any sigma, and this is a set of prime ideals, so then we can find an element x, so there exists x inside beta 1 such that x is not inside sigma of beta 2 for any sigma in the Galois group. Да? А это как бы заодно говорит следующее, да, что so equivalently applying sigma inverse we can say that there exists x inside beta 1 such that sigma of x is not inside beta 2. Yeah, so not I meant changing notation. Sigma inverse to sigma. То есть, у нас есть условие, что существует вот это вот давайте я напишу, so by prime avoidance theorem, lemma. Мы получили, что вот у нас есть множество идеалов, где бета-1 не может быть включена в них. Значит, существует элемент из бета-1 такой, что вот этот элемент не принадлежит никакому из элементов орбиты. Но с другой стороны, можно сигма перенести, сигма минус 1 применить. и получить, что у нас существует элемент такой, что сигма от x не принадлежит бета-2 для любого сигма из g. Ну, то есть я сигма минус 1 применил, а потом заменил сигма, ну, просто это обозначение. Да? Сигма на сигма минус 1. Ну, а давайте теперь как бы рассмотрим другой элемент. Хорошо, вот это мы запомнили. Давайте. So consider norm of sigma. Or norm of x. Norm under field extension, which is just the product of, ну, здесь как бы мы, so which is a product of all sets of Galois elements of sigma of x. And so note that norm of x so is written as x. So there is a unit element, of course, inside this product. So it can be written as follows. So sigma is not identity. So norm automatically belongs to ideal beta 1, because x was in beta 1. Yeah, so norm of x also is an element of beta 1. And notice that beta 2 is prime, and sigma x is not inside beta 2 for any sigma in G. In G. So this implies that a product is not in the prime ideal. So, ну, то есть, если у нас есть множество элементов, каждый из которых не принадлежит простому идеалу, то их произведение тоже не принадлежит простому идеалу. So, norm of x is not the element of beta 2. Yeah? But then notice that norm, so by Galois theory, so notice that sigma of norm of x is equal to sigma of just norm of x, just because application of sigma permutes the factors. Then it implies that norm of x is in K. But in the same time, notice that x was an element of B, so x is an integer over A, and if you apply sigma of x is the root of if you take the integer polynomial, so I do not specify which one. So you can apply sigma, and so sigma x is a root of the same polynomial. Because sigma is homomorphism and it preserves coefficients. Yeah? So ai are the elements from A which are inside K, and sigma of ai is equal to ai. So sigma x is also integer element. So the norm is a product of integer elements. So that means that norm is the element of is an element of B. Norm is integer over A. So norm is integer over A. Ну, то есть, как бы, что мы получили? Мы получили, so we have obtained the element that is inside the K, and in the same time it is integer over A. Since A is integrally closed, so since A is integrally closed, in its fraction field, then norm belongs to A. Yeah? But norm was an element of ideal beta 1, but norm of X was an element of beta 1. So it is the intersection of beta, it lies in the intersection of beta 1 and A, which is ideal P. But by assumption, norm of X was not inside beta 2. That is a contradiction. So this means that contradiction since beta 2 contains P, because beta 2 was just intersection of P was intersection of A and beta 2. Ну вот, поэтому мы, so this contradicts the assumption that beta 1 was not in the orbit of beta 2. So that proves our claim. And now we can, so this means that if you take a reducible variety and look at reducible variety line covariate, the Galois group permutes all these varieties in the preimage. And line cover means that you just take full preimage of your variety and take its reducible components, and each reducible component will be ideal, will correspond to ideal line covariate, and they are really permuted by the Galois group. And now we can finish the proof of going down theorem. So going down theorem. In Galois case. Yeah, so here you already, so you have the following situation. So you have P1, P0, and here you have beta 1 lying over P. Yes, so the idea is just to do the following, just to make, so the idea is to make an arbitrary choice, and we are going up theorem. And then you modify this choice by the action of the Galois group. Yeah, so by going up theorem, то есть идея такая, мы сейчас просто найдем, ну, вот, положим, возьмем какое-то бета 0, которое, возможно, не согласовано никак с бета 1, а потом его подправим так, чтобы попасть в бета 1. Ну, вот сейчас мы этим займемся. By going up theorem, so there exists beta 0 prime such that beta 0 intersection with A is equal to 0. Yeah? So, of course, yes, so again, by going up, applying going up again to the quotient, yeah. So there exists beta 1 tilde that such that beta 1 tilde contain beta 0 and lying so also prime. So and beta 1 tilde intersection with P1 with A is equal to P1. То есть мы просто начали, ну, с помощью going up просто начали достраивать вот эту вот диаграмму, как бы. Да, давайте я еще бета 0 объявлю бета 0 с тильдой, ну, потому что они как бы предварительные. То есть мы просто с помощью going up стали достраивать нашу диаграмму произвольным образом. Сначала бета 0 произвольно выбрали, потом бета 1. То есть, ну, как бы два приема. Now by не согласовано. Now by previous theorem, so since we are working in Galois case, so by previous theorem, there exists sigma in the Galois group such that, сейчас я подумаю, куда хочу перевести. Бета 1 я хочу, бета 1 с тильдой я хочу перевести в бета 1. That sigma of beta 1 tilde is equal to beta 1. Then I claim that the required beta 0 is just then put beta 0 is sigma beta tilde. То есть, смотрите, мы просто как бы делаем следующее. Мы берем произвольную цепочку, ну, над P1 у нас получается, мы можем бета 1 с тильдой перевести в бета 1, но значит, как бы мы переведем бета с тильдой в бета 0, который содержится в бета 1. Да? То есть, then beta 0 will be which is sigma of beta 0 tilde is contained in beta 1, which is sigma of beta 1 tilde. Yeah, so we can take beta 0 tilde is inside beta 1 tilde and apply sigma. Yeah, so you have this kind of equality, but sigma preserves K, so it fixes sigma of Pi is equal to I, So the condition for inclusion of PIs, so if beta I tilde contains pi, then sigma of beta I tilde also contains pi. That proves the claim. Да, ну вот как бы, ну да, давайте, да, тогда закончим на сегодня. Ну, в общем, мы, получается, да, тут еще, ну, как бы спрашивается, что делать, если расширение было несепарабельное. Ну, вот, если вам интересно, давайте я скажу на этом. So, if extension is not separable, is not separable, so we can do it as follows. So there is, то есть у нас теперь есть как бы L, в нем K. Но давайте L с чертой выберем также. То есть find L tilde as the set of roots, of all polynomials of alpha i's, and then you see the following. So you will have the following. So this extension will be normal, but not separable. And there will be, so you can consider the set of invariants of the Galois group. So G is the group of automorphisms of L tilde over K. And here you can consider the inseparable closure. So you can take the roots of 1 over Q, where Q is the power of characteristic. So just this is the field obtained by extracting pth power roots from elements и вот как бы можно заметить, что вот это, ну, то есть вот все, что могло быть несепарабельно здесь, ну вот над K, из внутри L, мы, так сказать, ликвидировали вот этим расширением. Поэтому вот K на 1 над Q, оно на самом деле совпадает с полем инвариантов вот этой группы автоморфизмов. Да, ну, во-первых, поскольку, да, тут есть важное замечание, поскольку извлечение в характеристике P, извлечение корней p-той степени единственное. So since in characteristic P the operation of solving just x p equal to y is unique, and so then if sigma fixes k, then sigma fixes the set of solutions here. So K1 over Q. Ну и вот это вот оказывается, ну вот это вот поле, да, оно оказывается полем инвариантов, и поэтому как бы, но чем отличается вот это поле от этого? Просто возведением в большую пятую степень. So so in the proof take norm in the Q power for large Q equal to P to the power n, and then you will get that norm of x. Norm of x belongs to the extracting Qth power root, and the norm itself will be integer over a, just norm in the power Q, and belong to K that will prove the claim. То есть как бы доказательство на самом деле одно и то же, просто ну, группа ГУА не трогает вот эту часть, которая получена вот этим расширением. Поэтому как бы... То есть это надо отдельно вот так проговаривать, но тем не менее это такое, ну, техническое чистое утверждение. Ну и в качестве упражнения можете подумать, как бы, а что происходит, когда у вас поле расширения, ну, бесконечно. То есть на самом деле, ну, как бы ваша ситуация сводится, ну, надо ее свести к конечному целому расширению. Ну, например, можно как бы работать с, ну, не с идеалом, например, а с конечным множеством его образующих множеств, в нетовом случае. Вот так. Ну ладно, давайте сегодня закончим. В следующий раз я хотел поговорить о теореме нормализации и о теореме Гильберта нуля.
А вы же куда-то сейчас сохраните конспект доски, да?
Да, но я не умею его как бы перекидывать.
Да, я поговорил с студентом, который обычно это делает. Он сказал, что можно куда-нибудь просто на компьютере сохранить, потом сказать ему куда.
Ну да. Ну вот я, я просто сегодняшнее число делаю.
Да, хорошо.
Скажи, пожалуйста, листок когда будет?
Ну, я надеюсь, уже вот все на этой неделе.
Хорошо.
Еще подскажите, пожалуйста, вот у вас, ну, в основном по АТЕ, да, вы идете?
Ну, в АТЕ, например, нету вот этой леммы.
Ага.
Ну, то есть, как бы в основном, да, смотрите АТИО, но потом будут, ну вот этой леммы нету, теоремы некоторой нормализации там тоже нету вроде. То есть это надо, ну если не будет непонятно, можно посмотреть, ну, наверное, в Мамфорде.
Угу. Который «Красная книга» или...
Да, ну вот теорема Гильберта о нулях точно в Мамфорде.
Ага, окей.
Надо посмотреть, а лемма Ньютона нормализация, я просто надеюсь, будет понятно. Не сложно.
Да, хорошо, спасибо.
Ага.